Hello everybody, my name is Akhilesh Balaji. In today's video, we'll be exploring the concept of fractals. Are fractals really what you think they are? Let's find out in today's video. Fractals are commonly described as self-similar shapes at all scales. This isn't entirely true. This may be true for certain shapes such as the Serpinski Triangle and the Mandelbrot set, but this isn't exactly what the founder of fractal geometry, Benoit Mandelbrot, had in mind. Mandelbrot said that fractal geometry was a model that roughness in nature could be based upon. Self-similar shapes are just a small category in the wide umbrella of fractal geometry. And Benoit Mandelbrot said that fractals or self-similar fractals are just a way to emulate the roughness in nature infinitely. This in a way is in direct defiance to the laws of calculus, which say that if you zoom in far enough into an object, it will appear smooth. In direct contradiction to this, Mandelbrot said that the further you zoom into an object, the more and more rough it gets. When we represent fractals visually, for example, if you see one printed on a piece of paper or see an image of one on your laptop, this isn't exactly a fractal because we have to give the computer a point to stop at when it renders the image. So what you see on the screen is actually an approximation of a fractal. If we went on forever, the computer would eventually crash because of the increasing complexity. Or if the computer was powerful enough, it would run on and on forever. Let's take an example to continue further. The Koch snowflake or the von Koch snowflake. Visualize this. You have two triangles overlaid on top of each other to form a star shape. Right? And the star has these 6 triangles jutting out of its edges. And visualize the same thing, another set of triangles being overlaid on these set of triangles, and again and again. You get the point. This goes on forever. Now think about this for a moment. If you tried to go and measure the von Koch snowflake's perimeter, it would go on forever because it had infinite iterations, correct? What a paradox. Here we have a shape that has an infinite perimeter yet a finite area. Think about that for a moment. To better familiarize ourselves with the concept of fractals, let's first redefine our understanding of dimensions. Yes, I did a video on dimensions earlier, but let's think about this concept in a new perspective. You may think you know what a dimension is. The 0th dimension is a point, the 1st dimension is a line, 2nd dimension is a plane, 3rd dimension is a cube, the 4th dimension is a tesseract, and so on and so forth. But what if I told you that the Koch snowflake was in fact a 1.26 dimensional object? Weird, right? How is that even possible? Let's find out. Let's start off with the simplest shape you can think of, a line. Now, a line is self-similar in a sense, right? Because you can break up a line into 2 other lines, and those 2 lines can be broken up into 2 more lines. And if we broke up a single line into 2 more lines, these lines would be half the length of the original line, and therefore have half the mass of the original line. Now, let's take a square. A square is also self-similar because you can break it up into 4 smaller squares, right? And you can visually see this because it takes 4 of the smaller squares to make up the bigger square. Therefore, a square that's half the area of the bigger square would be 1/4 the mass of the original square because it takes 4 smaller squares to make up the larger square. Let's do the same thing with a cube, right? A cube is also self-similar. It can be broken up into 8 different cubes that are half the volume of the original cube. and each of these smaller cubes has 1/8 the volume, the 1/8 the mass of the original cube. Do you see the pattern we're getting over here? The mass of a smaller line was half to the power of 1 of the original line. The mass of the smaller square was half to the power of 2 of the mass of the original square. The mass of the smaller cube was 1/2 to the power of 3 of the original cube. We'll get to that pattern in a while. For now, let's move on to the Serpinski triangle. A Serpinski triangle is, yes, what you see on the screen right now. As you can see, it consists of various triangles that follow a specific pattern as you zoom in infinitely. This Serpinski triangle is made up of 3 individual Serpinski triangles, which in turn are made up of 3 more individual Serpinski triangles. And each of these smaller Serpinski triangles is half the length or half the area of the original Serpinski triangle, but have 1/3 the mass of the original Serpinski triangle. But we don't know how to define the self-similar units that come together to form this Serpinski triangle, correct? We don't know what percentage or fraction of the original Serpinski triangle the smaller Serpinski triangles are. Now, the concept of dimensions also depends on the mass of the object. Let's think about this way, okay? We had the line that was one-dimensional. And if we cut that line in half, the smaller line was 1/2 to the power of 1, the mass of the original line, right? And we move on to the square. The square was cut, the smaller squares were half the length of the original square, therefore making it 1/4 the mass of the original square. 1/4 is nothing but 1/2 to the power of 2. Let's do the same thing with the cube. The cube was made up of 8 different smaller cubes, which makes the mass of one small cube 1/8 the mass of the original cube. This 1/8 can be rewritten as 1/2 to the power of 3. Do you see what I'm getting here? The dimension of an object is in fact the exponent that the scaling factor is raised to. Let's recap that for a moment. When you scale an object, its mass is that scaling factor raised to the power of the object's dimension. So, the mass of an individual Serpinski triangle would in fact be half raised to the power of its dimension, because we are scaling down the Serpinski triangle by half the value of the original Serpinski triangle and raising it to the power of its dimension, which yields us is its mass. And we already know the mass of a smaller Serpinski triangle, 1/3, because it takes 1/3, it takes 3 of those smaller Serpinski triangles to make up the larger one. Now, how do we find the Serpinski triangle's dimension? This is actually quite easy. This is the kind of things that logarithms were designed to do. So log base 2 of 3 would yield us the dimension of a Serpinski triangle. As always, a trusty scientific calculator always has the answer. Let's power it on, and you can see it over here. I'm going to key in log, which is over here. One second. Yes, the log and base 2 of 3. You can see that over there. Log base 2 of 3. And when we hit the equals key, we have the dimension of a Serpinski triangle. 1.5849625001. Approximately 1.85. How cool is that, right? We found the dimension of a Serpinski triangle. Now, a Serpinski triangle may seem two-dimensional, but it's in fact a fractional dimension, 1.85. This explains why if you tried to measure its length would turn out to be infinity, and if you tried measuring its area would be 0. because there is in fact an infinite amount of negative space as well as an infinite amount of positive space inside the Serpinski triangle. So neither length nor area are fitting terms to describe it. Let's take this one step further. Most two-dimensional shapes aren't in fact self-similar. Take for example a circle. We know that a circle's dimension is 2. But then no matter how you try to piece together 4 of these smaller circles, which are half the area of the original circle together, you can't seem to get that right mix to get the larger circle, right? So how did we end up with its dimension? The answer lies in a grid. If we take a small circle and we place it on a grid and we count the number of boxes that are touching the circle, right? And we take that as one value. Next, we scale up the circle by some factor, let's say 2, right? We scale it up to twice its original size. And then we count the number of boxes that are touching it again. And we divide the original number by the second number. And we get approximately 3 point something something. So approximately 4, right? And what's the square root of 4? 2. The finer and finer you make the grid, the closer and closer your value will get to 4. And likewise, the closer and closer your value will get to 2. But because we're using a grid over here, we can never get the exact amount. You guessed it, you can do the same thing with any non-self-similar shape. The coastline of Britain turns out to be 1.21 dimensional. You can try this with any shape and you will get its exact dimension. How cool is that, right? But remember, because we're using a grid, you can never be sure of what its exact dimension is. Now then, on to the main question. What is a fractal? Well, a fractal is a shape that never gets smooth, no matter how much you zoom into it, as opposed to being self-similar, which is just a part of that notion of never getting smooth, right? Because of this, it has a length of infinity and an area and volume of 0, right? Typically, a fractal's dimension is not a whole number because of all the properties I mentioned above. A fractal has both an infinite amount of negative space and an infinite amount of positive space. The field of fractal geometry keeps evolving every day, but you can play with fractals in your own backyard. Have you ever seen any of those ferns growing around? Well, they are nature's version of a fractal. Unfortunately, like I mentioned earlier, these fractals have to end at some point. They're not infinite. These fractals have to stop at some point, but not the ones in your head. Stay curious, stay safe, stay home. See you in the next video.